Okay, so the next thing we want to look at is when we have a blow up of a single point, then we see, for example, in when we blow up AN at the origin, that this replaces the origin by this Pn minus 1. This we have seen in examples. And in this case here, we started with something of irreducible of dimension n, and then we have seen, because this thing is defined as a closure of an open subset, this is still irreducible of dimension n. And this here, the pre-image of the locus we blew up, this we called the exceptional set. And this turns out to be of dimension n minus 1, so of codimension 1. And this is not just an accident in this case, but this is a general phenomenon. And this is the big proposition that we want to show here, namely that the dimension of this exceptional set is always 1 less than the total dimension. So to formulate this, we formulate this in this case of affine blowups. So if x is affine and we have R functions on x, then we define pi, the blowup x tilde to x, at these functions. This we have seen some videos ago. And then the claim is every irreducible component of E of this exceptional locus, which is the pre-image under this map pi of the vanishing locus of all of these functions here, that this has codimension 1 in this x tilde. And therefore, we also call it the exceptional hypersurface. And then from different contexts, something we haven't seen yet is that sometimes you also call it the exceptional divisor. That's the more common thing in the literature. Okay, and so let's start the proof. And in the proof, so we'll restrict first of all to some open subset and show it there. Namely, we have that the x tilde, the blowup, is always contained in this x cross PR minus 1 for these affine blowups. And this PR minus 1, of course, has the usual affine cover by the UI. And well, this is a statement that every component has a certain codimension. So it suffices to check this for each of the elements in this open cover. And so somehow we cover this x tilde by intersecting it with these x cross UI. And this thing we call VI. Okay, and then we start. So somehow then we have a diagram like this. We have the VI, and of course this still sits over X. This is somehow pi restricted to this open set VI. And then we have seen in the description of the affine blowup that this sits inside some subset. Let me call this WI. And this is now this subset of X comma Y in X, and normally I would write here X cross P R minus 1, but now we are in this subset UI, since we restricted to UI everywhere. And this was cut out by these equations, which told us that yk times fj of x equals yj times fk of x for all j and k. So this was, we didn't quite manage to always describe what the x tilde is, but certainly somehow we have seen this inclusion here. This must always hold. Okay, so let's call this thing star, and then now we need to well, we want to show that the pre-image, so somehow x tilde is covered by the VI. And now we want to cover this pre-image E of this vanishing locus here by these VI intersected it, and then show that it's of codimension 1 in VI. So basically, we want to show this by showing that it's a zero locus of a function, because we have seen when you impose a zero locus of a single function, then this has codimension 1. So this is our strategy. And to do this, we now need to make some claims relating this to the vanishing locus of a function. And the first claim here is that indeed, the inverse image pi x inverse of this vanishing locus of all of these functions is equal to the vanishing locus of a single function, first of all, on the wi. And the single function that we take is this fi. Remember, vi was this locus where the ith coordinate on pi minus 1 is non-zero, and we claim that on this open chart, we have the single function fi, and this cuts this thing out. And here I should mention, so somehow what do I mean by the function fi on wi? Well, w has these coordinates x comma y, and this is just a function which sends x comma y to fi of x. We just ignore the second coordinate. And to see the proof, well, we apply this equality star here for k equals to I. And remember, on this ui on this chart where yi is not equal to 0, when we identify this with an affine space, we just set so yi is equal to 1 on this vi. And so somehow on, I guess, on ui. And so so we plug this in, and then we have the yk, which is yi in this case. So this is 1 times fj of x is equal to yj times fi of x. And so this shows a very nice thing, namely, well, in this equality that we want to show, kind of one direction is obvious, because here on the left-hand side, we impose all of these vanishings. f1 up to fr should be 0, right? And here we just impose one, namely that the fi is 0. But then if we have this equality here, then we see whenever we have fi of x equals to 0, this automatically shows that fj of x is equal to 0 for all j. And then this means, so somehow one inclusion, namely this inside here, is always clear. And on the other hand, if we are here, then fi is equal to 0. And then this equality shows that also all of the other fj are 0. And so we are also here. So this shows the other inclusion. And this concludes this one here. Okay. And so this is the proof of the claim. And so at least somehow on this wi, the pre-image of the locus we blow up is cut out by a single equation. And then we turn this over to here. So then the claim is that the thing that we're actually interested in is the pre-image of this 0 locus on vi. So we intersect this thing with vi, and then we can compute this the pre-image via wi in this diagram. So somehow if you take the pre-image of this locus here, well, you can as well take first the pre-image here and then intersect with the vi. Okay, and then somehow then the claim tells us that this thing is equal to the wi of fi intersected vi, but fi is just a function on x, so this still makes sense. So somehow to see it as a function on the vi, and so this is just the same thing as taking the vanishing locus of this function on vi. Okay, and so we have this exceptional set intersected vi is the vanishing locus of a single function. Now the only thing that we need to check, the final thing to complete the proof, is that this function is non-zero, because if it was a 0 function, then it wouldn't actually cut down the dimension by 1. That wouldn't be nice. So we need to check this final claim, And this is then claim 2. That, well, if the VI is non-empty, the claim is that Fi is not equal to 0 on Vi. I mean, if Vi is empty, then we don't have to show anything because, I mean, we just have to show all the exceptional components have some dimension. And then if Vi is empty, then, well, this just doesn't contribute. This is not a problem. And we don't have to do anything in this case. And so if this is non-empty, then it's actually not the 0 function. And so the proof is that otherwise, well, otherwise, if Fi was 0 on Vi, then here we would just get all of Vi, right? And then we would see somehow Vi is equal to Vi intersected this pre-image here, which would just mean that Vi must be contained in this pre-image here. In other words, pi or pi x sends Vi to this vanishing locus, right? So somehow pi of Vi subset the vanishing locus. But then this would show that pi of all of x tilde, because x tilde is irreducible, the Vi is a non-empty open subset. And so this is just given by the closure of this. Here we use this condition that Vi is non-empty, and it's non-empty open subset in this irreducible space, so it's dense. And then this here, after taking the closure, you will still have this containment, right? Yeah. But then now we're in business because then the whole blow-up actually sits inside the exceptional locus, which means the complement of the exceptional locus, so U is equal to the empty set, but somehow U x tilde is also just the closure of U. And so this would also be the empty set, and this is a contradiction. We assumed that not everything that we talk about is the empty set. It was one of the assumptions. Okay, so this was like a little argument that we still needed to fill in to at least check that this is not the 0 function. And now we have everything assembled, because then by Kroll's principal ideal theorem, we have seen that the vanishing locus here, so Fi is of pure codimension 1 in Vi. And then, well, we have also seen again here, this here and this here have the same dimension because the Vi is a dense open subset here. So it has pure codimension 1 in here. So this means it also has kind of pure codimension 1 with respect to the dimension of x tilde. And this is what we wanted to show. So this finishes. This finishes the proof. And so these exceptional sets tend to have codimension 1. And as a consequence, we can also compute the dimension of this tangent cone to a variety x that we have seen in this in the last video. And this is this corollary here, which says if x is a variety and a is an x, then the dimension of the tangent cone at x is just given by the codimension of the single point inside x. And this also we call the local dimension of x at a. And this all kind of makes sense because we invented the tangent cones to study x locally at a. And so their dimension should better be the same thing as the local dimension of x at a. For the proof, I just want to recall one exercise which computed this codimension here when x is not necessarily irreducible. because we don't have any irreducibility assumption here. And this exercise is saying that if X is an affine variety and it has such an irreducible decomposition and A is some element there, then the codimension of the single point set at X is just the maximum of the dimensions of the components which contain A. This also kind of makes sense, but we wanted to recall it here. And then the proof of this corollary. So most of the parts are not so difficult, so I just go through them like this. So the first one is we don't want any unnecessary complications. And so, well, you see the input a priori is a variety. But then the first thing that we can do is for any irreducible component of X which does not meet A, so somehow A is somewhere and then there's some exceptional component disjoint from it, we can just remove all of these finitely many components. This goes to an open subset. And kind of the tangent cone only depends on what we do in a small open subset of A. And so we can throw all of these components out which don't meet A. That's the first step. So we can assume in the first step that all the irreducible components of X actually meet A. Fine. And then the second thing, we already restricted to an open subset. By going to an even smaller open subset, we can assume that this subset is affine, so it sits inside some affine space AN. Okay. So these are the two assumptions which we can have from the start. Also, we exclude one trivial case. If X is just a single point set, that's a fine variety. But in this case, we don't really have to do anything. The tangent cone is zero-dimensional, X is zero-dimensional, everything works. So we can exclude this case here. Okay. This was a bit of general nonsense at the beginning, and then now we just write down for this affine variety, we write down irreducible decomposition like this. And the fact that X is not the one-point set then actually implies that all of these have to have dimension at least 1. Because otherwise, if you had a dimension 0 set containing A, then this Xi would already be all of A. But then, because A is by assumption contained in all of the Xi, but then you couldn't have any other components like this. So you would have just a single component, and then we would be in this trivial case. Okay, so we can assume that the dimension of Xi is at least 1. And then the proposition tells us that the exceptional set of the blow-up, this was the proposition that we just proved, the exceptional set of this blow-up here is of pure dimension dim Xi minus 1 inside here. So this is just the blow-up of the ith irreducible component. And then, well, the blow-up of all of these things is just the union of the blow-ups of the irreducible components. And then what we do to get the CA of the Xi, remember, this is just a cone over the exceptional set. And so if the exceptional set has this dimension here, this is the projective variety of this dimension, then there was another exercise that if you take the cone over projective variety, the dimension goes up by 1. So this cone here has pure dimension dim of Xi. Okay, so nothing really interesting happened here. We just observed, first of all, we applied the proposition to compute the dimension of the exceptional set. And then when you go to the tangent cone, when you take the cone over this, the dimension goes up by 1. So this gets rid of the minus 1 again. And then, well, what you do to calculate the dimension of CA of X, well, it's just the maximum dimension of all of its components. So of the CA of Xi, but their dimensions are given by the dimension of Xi. And then here, this was the exercise. The maximal dimension of irreducible components meeting A is exactly the codimension here. So this gives the codimension there. Okay. So the one thing that we secretly used in this argument and that we should justify is that this exceptional set here is non-empty, because the formulation, if you look closely at the proposition, it says that every irreducible component of the exceptional set has some dimension, but we don't know if it was empty, then we would have fewer of the things in this maximum, and then maybe we wouldn't get the right number. That wouldn't be good. So what we should still do is we should show that this exceptional set is non-empty. Okay, and for this, well, this I want to explain again in some more detail. So somehow note that we always start with this open set U, which is just the xi minus the point we blow up. And then, well, the one assumption that we haven't used yet, that we argued before, is that we can use this dim of xi greater or equal 1. In particular, this means that U is not the empty set. That's the one place where we use it, right? Because if U was the empty set, then xi would just be A. That would be a contradiction. So somehow this thing is not the empty set. And then we have a non-empty open subset of this irreducible component xi, and that we use many times, that the closure is then everything. Okay. Let me circle this, and this we're going to use in a second. Let me also give it a name. And then by the definition of the x tilde, well, we have that the x tilde, xi tilde, is given by the closure of U inside of this xi cross p n minus 1. And everything sits inside here. So let me call this projection to xi. Let me call this pi tilde. And let me call this projection here, as usual, pi. Okay. And now we want to argue that it's not possible that that the fiber of that the fiber of A here is empty. Okay. Now we can actually use a very nice callback to something which we have seen before, namely this thing which we have seen is that pi tilde, this projection map on the right, is a closed map. And this was the definition that this thing here is closed. This followed from the definition of Pn minus 1 being complete. And we have seen that this is the case. So if you recall, this was a kind of technical thing, that the projection from X cross the variety to X is always a closed map. And okay, so where does this all come together? Well, the fact that this is a closed map then shows, well, this here was defined as a closure inside here, so x tilde is closed in there. So this shows that then pi of xi tilde is closed in xi. And also, one thing, I mean, this was defined as the closure of U. U sits inside here as an empty open set. And this map was an isomorphism over U. That's always the case for the blow-up, right? Away from the center of the blow-up, you're an isomorphism. So this means this thing here also contains pi of U, which is just U. So there was this isomorphism, U, one sitting above and one sitting downstairs. And then, well, we have that U is dense inside xi. And so since this is a closed set, we have that the xi tilde. So this must actually be surjective, this blow up in this case. So we get everything. And so in particular, what we wanted is that the exceptional locus, which is the pre-image of the blow up center, is non-empty. Because if you have a surjective map, you take the preimage of a non-empty set, it's still non-empty. Okay, so that finishes the proof. So what we have now seen is that there's a very nice link between the dimension of this cone of x at A and the local dimension of x at A. And this will be important in the next chapter when we talk about smooth varieties.